All right, moving on with the next conic section. Going to look at ellipses here. Ellipses are probably what you've called ovals in the past, but they're actually ellipses. Things to know about the ellipse is first it has two foci. I pronounce it foci. A lot of people pronounce it foci. I looked it up and apparently both of them are acceptable, but I'm going to say foci because I like that better. Deal with it. Um, uh, an ellipse, the way an ellipse is defined is you have two foci, and then the ellipse is the set of all points such that you can read the technical definition. But what the ellipse really is, and what this little sentence right here means, is that if I start at one focus and I draw a line to any point on the ellipse, and then draw it to this point, draw that, and then connect that point to the other focus, if I add these two distances together, that distance, we'll just call it A, and this distance, the sum of those two difference is always the same. So let's throw in some real numbers just to make it a little bit easier to understand. If this distance right here is 3 and this distance is 5, that's an overall distance of 8. That was a funny looking 5. We're going to stick with it though. If I were to draw a line here, and then back here, and then let's say we know that this distance right here is 1, well, the two lengths have to add up to 8. So if this one's 1, this one has to be 7. The sum of those distance always has to be the same. That was kind of a bad example, but whatever. I'll do one more, just for the sake of doing one more. If I draw one, say right here, we'll call that distance 2. Then this distance right here would have to be 6. So if this is 2, this one right here would be 6. I'm going to have to move that 7 because it's confusing. There. So the sum of the distances is always the same. Another interesting fact about an ellipse is if you are able to build a room that is a perfect ellipse, meaning we're kind of sitting here, pretend this is a room and we're hovering down, and the walls along the side of the room formed an ellipse, if one person was standing on this focus right here, and another person was standing on this focus right here, anything this person says is going to bounce off the walls and be redirected perfectly to that other focus. And same thing for this one. And there are actually rooms in museums built around the world where they have an elliptical room like this, and they mark the two foci, and even though there may be people standing in the middle right here, what you can actually do is you can stand on one focus, this person can stand on the other focus, and y'all can actually whisper to each other and hear each other, but these people in the middle won't be able to hear you because they're not standing on the focus. So just a little interesting factoid with ellipses that I think is kind of cool. So there we go. Let's move on to other stuff with ellipses. The standard form for an ellipse looks like this. It's x minus h squared. You can read it. One thing to know about an ellipse is you will add the two fractions. If you see a minus sign right there, that's actually a hyperbola, which we're going to talk about later. In the ellipse, the way I do the ellipse is I think a is always the bigger number, and it does need to equal 1. If the bigger number is under x, if it's x minus h squared and the a squared, the larger number is under x, that means you're going to go further left and right than you do up and down. We will lovingly and affectionately call this a Stewie Griffin. So it kind of has that Stewie Griffin with lowercase s and g. Has that Stewie Griffin orientation, goes left and right. If the large number is under the y-axis goes up and down, so this ellipse goes up and down. We'll call this a VeggieTale. Just the y-axis goes up and down, so if the large number is under the y, the ellipse goes up and down. So there we go. Those are the standard forms for an ellipse. You do need to remember this little formula right here, a squared minus b squared equals c squared. Kind of like Pythagorean theorem, except you subtract instead of add. That's going to come in handy later. The map for making your ellipse, just like with your vertex in the parabola, which was hk, the center for your ellipse is hk. So the very center, this is going to be the ordered pair hk. And everything is hinged off that center. You move from that point to get to every other point in the ellipse. The vertices, I think, are the easiest ones to get to. And to get to your vertices, you move A and B to the left and to the right. Um, so if the way I remember this is if A right here, A is under the X. Since X moves left and right, I need to move A units left and right because it's under the X-axis. So that means this distance right here, that whole distance is A, and I'm going to erase my HK. This whole distance is A. Since A was under the X, we go left and right A. Here, B is under the Y, so I'm going to go up and down Y because my Y-axis runs up and down. So from my center, I'll go up B units, and I'll go down B units. And so this, whoa, that's not what I wanted. Let's get my marker, pen, there we go. So this distance right here is B, and this distance is B. That's a funny looking squiggle. There we go. And then finally, C is always the distance from center to focus, and that's going to be true for hyperbolas as well. So the distance from the center to a focus right here, that is a distance of C. Now I've just kind of muddied this thing up and I have stuff going all over the place. If you look at the Y one, in this one, A, the larger number, is under Y. Since A is under the Y, that's how far left and right, I'm sorry, up and down. The Y-axis goes up and down, so I'm going to go A units up and A units down. So from the center, I would go A units up and A units down. It all just depends on what number is under the Y. So I went A units up, and I went A units down from the center. And going left and right, since B is under the X, X goes left and right, I would go B units left and right. So this distance right here is B, and this distance right here is B. And then same as before, you go C units to get to the foci. So C units to that focus, C units to that focus, and the center is always HK. So you really look under the X and the Y to determine how far up and down or left and right you go. And you find C, which remember A squared minus B squared equals C squared. That's how we find C. And that gets us to the focus. So there's your general map for graphing an ellipse. And then finally, a little bit of vocab to go with the ellipse. You have the center, which I think the center is self-explanatory. You have vertices, which are the extreme top, right, left, right, top and bottom of the ellipse, major and minor axis, and eccentricity. Let me draw an ellipse in here. There we go. So I have that ellipse, and the center, which I think is obvious, the center, wait, hold my pen. Ah, it's being stupid. Okay, there's my center. It's HK. Your foci sit somewhere inside. Now the foci are always going to be oriented on the long dimension of your ellipse. So this ellipse is going up and down, so my foci will go up and down. There's a focus. This is a focus. And then your vertices are your extreme top, bottom, left, and right. I call all four of those vertices. There are a few books that only consider the ones that are further apart, the vertices. I think they are all vertices, and I'm going to stick with it. Your major and minor axis. Okay, the major axis is the long distance across your ellipse. I want to make that dotted. But that long distance, whatever the longer distance is between vertices, that is your major axis. Your minor axis is the shorter distance between vertices. So whichever vertices are closer together, that distance is your minor axis. So we'll call this the major axis in blue, and it goes the entire dimension, the entire length from top to bottom, and this green one we'll call the minor axis. Eccentricity, you can't really label eccentricity, but all eccentricity does, or eccentricity, however you want to pronounce it, it's a number that kind of tells you how close to being a circle the ellipse is. A circle has an eccentricity of 0, so when you find the eccentricity of an ellipse, you will get something between 0 and 1. If it's closer to 0, then our ellipse is more round. It's going to look more circular. I cannot spell circular. And technically, a parabola has an eccentricity of 1. But I'm just going to say if you're closer to 1, then you are non-circular. We'll just leave it at that. I'm going to leave it as Carboni terms. Who cares about what it's actually called? All right, so you have circular or non-circular, and the eccentricity of an ellipse is going to be somewhere in that range. So there's all that. Let's do one with real numbers because the notes are kind of confusing. Wow, 10 minutes on that. That's exciting. Hey, I do believe that ellipses are a lot easier than parabolas. First thing I'm going to do with all of these is I'm going to start by finding the center. So I'm going to go with the center, and the center is the same way you find the center of a parabola. With the x, I see x plus 1, so my x coordinate is -1. You change the sign. With the y is -2, but I'm going to change the sign and make that +2. So my center is -1, 2. Then I'm going to find my a and my b. My a is the larger number, and I notice that underneath my x is 25. 25 is 5 squared. That means a is equal to 5. And then I look under my y term, my smaller number is 9. 9 is 3 squared. Therefore, b is equal to 3. And let's go ahead and sketch this in here. Let me get my axes going. There we go. And I am going to start by graphing my center at -1, 2. So there's the center, and everything I do for this graph is going to be based on that point. Underneath my x is 5 squared. That means since it's under my x-axis runs left and right. Therefore, I'm going to go left and right 5 units from this point. So I'm going to go 1, 2, 3, 4, 5. And then I'll go 1, 2, 3, 4, 5. Under my y-axis runs up and down. So that means I'm going to go up and down 3 because 3 squared is under the y. So I'll go up 3 and I'm going to go down 3. And those are the vertices of my ellipse. So now I can go ahead and graph my ellipse, and it's going to look like this. I'm going to graph it in blue. And this is what the ellipse for this problem is going to look like. Good? Good, good. So graphing the ellipse is actually pretty straightforward. It's not too bad. And then once you graph it, I want you to find the vertices, the major axis, the minor axis, the foci, and the eccentricity. So let's start with vertices. I'm going to use the same thought process I used in locating points for my parabola. Let's see, I went left and right 5 units. I started at -1. If you move left and right, that changes the x coordinate. So -1, and then I went left 5 and I went right 5. So I'm going to do plus and minus 5 units from -1 to. Okay, that's actually going to get me both my far left and my far right. I start at -1, I go left 5, there's the -5, then I go right 5, there's the +5. I also went up and down. Now up and down is going to change my y coordinate, so that's going to leave my x's alone, but then from my center point of 2, I went up and I went down 3 units. And I'm perfectly okay if you leave your answers in this form. If you want to clean it up, you could also say your vertices are -1 plus 5, which is 4, 2. -1 minus 5 is -6, 2. And then -1, 2 plus 3 is 5. And -1, 2 minus 3 is -1. And those are the 4 vertices of this ellipse. Okay, now I need to find the foci. I want the coordinates of the foci. Now to get the focus, or the foci, I've got to find c. And remember, a squared minus b squared equals c squared, so we'll solve it that way. A squared is 25 minus b squared, which is 9, equals c squared. 25 minus 9 is 16, which means my c is going to be 4. Now that doesn't tell me what my focus is. C helps me get to the focus, and that means from my center, my ellipse is going left and right, so from my center, I need to go left 4, there's one focus, and I need to go right 2, 3, 4, there's another focus. And if I go left and right, that means my foci change the x-coordinate. I started at an x-coordinate of -1, and then I went right and left 4 units. And then my y-coordinate didn't change. I didn't move up or down, so my y-coordinate's going to remain 2. And I'm okay if you leave it like that. You could also do -1 plus 4 is 3, y-coordinate is 2, and -1 minus 4 is -5 with the y-coordinate of 2. So we have center, vertices, foci. Okay, minor and major axis. My major axis, that's the distance between my 2 longer vertices. And I think from the center, I went left 5 and I went right 5. So my major axis is going to be 2 times 5, or 10. That's the distance from my far left to my far right. My minor axis, is I went up 3 and down 3, so the short distance between vertices is 2 times 3, which is 6. So there's my minor axis. And then eccentricity, which I'll just label ECC. I'll go ahead and write it out. Eccentricity is C over A. My C value was 4. My A value is 5. So my eccentricity is 4/5, or if you want to say that's 0.8, you can call it 0.8, but that's your eccentricity. And remember, a parabola's or an ellipse's eccentricity is always going to be between 0 and 1. So there is our ellipse graph. Now let's do another one. This problem, x squared over 16 plus, well, you can read it. I'm going to start just like before, finding the center of this ellipse. And this one confuses people because there's not a number inside with the x. Now people will say, oh, well, it's y plus 3, so the y-coordinate's definitely -3. If there is not a number inside with the x, then the x-coordinate of the center is 0, -3. So let me graph that real quick. There we go. There's my center. And then I'll look under my x and my y. Under x, I see 16. 16 is 4 squared. Under my y, I see 36. 36 is 6 squared. Well, 4 is under my x. X-axis runs left and right. That means I'm going to go left and right 4 units. So right 4, and I'll go left 4. Under my y is a 6 squared. My y-axis goes up and down. So I will go up and down 6 units. So up 2, 3, 4, 5, 6. Down 2, 3, 4, 5, 6. And there are the points I needed to graph this ellipse. So let me graph this ellipse right here. I'll do it in blue again. I said blue. Give me blue. Thank you. And there's the ellipse for this problem. Okay, good? Good. Then from there we find the rest. Now I'm going to go through these kind of fast because this video is getting longer than I wanted it to be. So center, my vertices. My x coordinates under x was 4, so I went right and I went left 4 units. My y coordinate didn't change when I moved left and right. And then I went up and down, so from my y coordinate of -3, I went up and down 6 units. And I'm just going to leave it like that. To get my foci, I need to find my c. So that's going to be a squared minus b squared. A squared is 36 minus b squared is 16 equals c squared. That's 20 equals c squared. Square root of 20 equals c. Whoops, that's not a c. And c, that cleans up to 2 square root of 5 for my c. And then I'm also going to kind of think, well, square root of 20 in the back of my mind, I know that 4 squared is 16. 5 squared is 25. So 20 is going to be somewhere between 4 and 5. So I'm going to say that's about 4 point, I'm just guessing, 4.5-ish. I don't know. That's a guess. And I really only need to have a ballpark figure for this graph, because when I graph my foci, I know now that I need to go up 2, 3, 4, and a little bit more. So I'm going to have one focus around here, down 2, 3, 4, and a little bit more. There's my other focus. The main thing I need to remember is that my foci went up and down. That's going to change my y-coordinate. So I started at -3, I went up, and I went down 2 square root of 5. Major axis, the long distance between vertices. I went up 6 and down 6, so that's 2 distances of 6, which is 12. Minor axis, I went left and right 4 units, so that's 2 distances of 4, which is 8. And then my eccentricity is c over a. C is 2 square root of 5, and a is 4. No, it's not. A is the larger number. A is 6. There we go. It may be a good idea for you to identify your A's and B's at the beginning. I didn't do it this time. A is 6 and B is going to be 4. And then this right here is A squared minus B squared equals C squared. So there is that ellipse. And then the one more thing I wanted to do, and I'm not going to complete this problem. I'm going to do this as quickly as possible because I've already hit the time limit where you quit paying attention. We need to get these. Some of these are not going to be in standard form. And so the last thing that I'm going to show you is how to get an ellipse in standard form that is not in standard form to begin with. We are going to have to complete the square, just like we did with parabolas. And I start by grouping my like variables. So I have 4x squared and negative 24x. And then I have a positive y squared and a 4y. And then I'm going to take this 24 and I'm going to move it over. I'm going to take that and just move it to the other side and make it equals negative 24. The constant is going to get moved over. Then I'll group my x's, I'll group my y's, and I have to complete the square. Now the y's are actually ready to go. I have y squared plus 4y. I'll leave some space to complete the square. But with the x's, you need to factor out that 4. I'm going to start by pulling out the 4, and that'll give me x squared minus 6x, leave some room to complete the square. And now I need to add something to my x's, and I need to add something to my y's to give me a perfect square. And you do that by taking half of the middle number, and you square it. Half of negative 6 is negative 3. Negative 3 squared is 9. Half of positive 4 is positive 2. 2 squared is 4. But if you add something to the left side, you have to add it to the right side. Right here, I added 4, so I'm going to have to add 4. Now, the tricky part is it looks like I added 9 to my x's, but remember, anything inside these parentheses is being multiplied by 4. So it looks like a 9, but it's really 4 times 9. And 4 times 9 is 36. So I actually need to add 36 to this side. So once you complete the square, you add to the other side to counter what you added to the left side. Now we factor these. It's x minus 3 squared plus y squared plus 4y plus 4 factors to y plus 2 squared. And that's why I write this middle step, minus 3, x minus 3 squared. I squared a positive 2, y plus 2 squared. And all that equals, this is going to equal 16 when you combine all of these things right here. All of those equal 16. And then the very last step we're going to do to finish getting this into standard form is we're going to divide by 16 all the way through, because you need your ellipse to equal 1. Your standard form, it equals 1. So to get 1, I'll divide by 16. 16 divided by 16 is 1. Over here, 4 goes into 16 4 times, leaving you with x minus 3 squared over 4 plus y plus 2 squared over 16 equals 1. So that's in standard form. I'm not going to bother graphing it because I've done so much already. I am going to put, I am going to put number 3 here in standard form. I'm simply going to pause it and work it out and slap the answer up here. So it's going to be like a 10-second wait for you, if that long. But anyway, I just want to show you what this one looks like when you put it in standard form too. One thing I do want to mention about this problem, there was no just y term. Like I had an x squared and an x term. I'm going to need to complete the square with my x's, but since there's only a y squared term and nothing else, we actually don't have to play with the y squared term. We're just going to leave that as it is, and it's going to come along for the ride throughout the problem. So I'm going to pause it and finish working this out. I just wanted to point that out, what to do if you only have one squared variable for either x or y. There we go. So now that one's finished, just in case y'all are feeling studious and want to work this one out on your own. So you now have the answer to get that one in standard form. Then from this point, you would find the center, the vertices, foci, A, B, C, and all that good stuff. So there you go, 25-minute video. Yay!